is it physically possible, is it economically viable to buy a 3D printer and use it in your own home if we're only considering toys? So here's some examples of 3D printable toys that are in the open source repositories today. And what I wanted to do is just give you a feel for it visually of what's possible with one of these cheap 3D printers today. So this is a little chest set, a travel set, 16 bucks on Amazon, $2 if you print it yourself. Quality, basically equivalent. This is a Toys R Us $15 little puzzle. You can see that the 3D printed one isn't quite as good because the person that made that particular one didn't take the time to change the filament and put it in different colors, so it wasn't quite as good. But you're saving 88% of the cost for doing it at home, and in terms of the actual functionality of the toy, I'm not sure that there's any difference. These are, again, a Tonka truck, $7. 3D printable one, $2. You know, we can get in an argument about whether it's an exact equivalent because it's a different type of truck, but trust me, if you really need a city sanitation truck, I'm sure that there's already a 3D printable open source one available on the web. And it's just not the mass manufactured toys. Also, these toys that are being sold on Etsy, like these little puzzle blocks, again, come with substantial savings, are functionally equivalent. There's also wood filament already available on the market that is between 10% and 30% wood. And so if you print with it, it smells like wood. You can stain it, you can paint it, you can sand it. It looks, for all intents and purposes, like wood, even though it's mostly plastic. And you can start to see the potential to make better products just from doing something as simple as a color change and get substantial savings. And so to go through the woodworking and making one of these little math puzzle things, it's 25 bucks, takes some real, honest to goodness time, whereas setting up the printer to print one out, it takes almost no time. Then you can start to make more complicated toys. So this is comparing a Captain America toy to, I think that's Bloodshot. And it's the savings aren't as high because it's a more complicated print. Now in this particular case, the comic book publisher commissioned this Bloodshot toy because they hadn't found a partner yet. Maybe somebody in the audience would be a good partner for them to start mass manufacturing their toy. What they wanted to do was to create additional market for their comic book by having things that kids could print out and play with. And so you could say the value of the Captain America toy might be worth more because it's a more popular character, but the ability to CAD a Captain America toy is basically functional equivalent to that Bloodshot toy. There also happens to be, there's a professor again in the United States that has made an extremely exquisite, articulated action figure that you can customize. So it's set up so that you can then make it your own figure, has many more joints, it's more functional than what's available on the market. Okay, so this is maybe possible, but does that mean anybody's actually doing it? So to figure out if that's true, I did another study where I partnered with My Mini Factory. Now My Mini Factory is a British company whose business plan is to have a repository of open source 3D printable designs. And I need to point out that the study is just on one company, but there are dozens of these 3D printing repositories out and available now. There are already millions of designs. So I'm just looking at a very tiny sliver, a small fraction of what's already available on the web. So it turns out that there actually are quite a few people doing this. So we looked at 4 different types of filaments, and I'll show you that in a second. But the gist of it was the savings, when we're only considering toys, only from one repository, and only during 1 month, was 75% over commercially available toys using the most expensive filament, 90% with the least expensive. Overall, from this one repository, extrapolating to a year, there was $60 million of offset purchases. Now, probably most of the people in the audience, $60 million is your rounding error, but this is the beginning. It's only one repository. It was only 100 toys. That was just the data from one place. There's many, many more places that are using this. Many, many more 3D printers are being sold. And we already got roughly a factor of 3 increase from when this paper was published to 6 months later. And so even that one repository is seeing more traffic. Of the designs that people were downloading, there were many things there where there was a commercial equivalent. But there are many things that are not commercially available, and sometimes that commercial non-availability is due to intellectual property problems. And so it's very difficult, for example, to make a Lego / Lincoln Log piece because they're owned by different companies that don't have anything to do with each other. Similarly, there's things that people might want that haven't hit the market yet, like Game of Thrones is a very popular show, and there was no Game of Thrones dice cup. You can't buy that, but somebody made one, made it freely available, and then became very popular as people started to download it. Let's take an iconic toy for a second, the humble Lego block. Lego makes quite a bit of money selling ABS extruded plastic, and they're good toys. I know I like them, my kids like them. And the average cost for a Lego toy is about 6 cents. A generic Lego costs about 3 cents, so you could absolutely save money by going to the generic. And then if you look at the 3D printed one using commercial filament, it's 5.8 cents, and so it saves you a little bit off of a Lego brand block, but it's probably not worth doing, and you're losing money if you're not buying a generic one. If you print from pellets that are readily available on the web, that drops it down to 1.4 cents, and so now consumers might start thinking about doing it. There are already pellet extruders on the market, and there are also extruders that then make filament that you push in. They are not nearly as widespread as the 3D printers are. And you could say, well, if you look at a rapidly printed 3D printed ABS part, and it's a little bit hard to see here on the thing, but you can almost make out the Z-step lines, where it's done one thing and then moved up. You can see that line. Well, if you're printing an ABS, you can just wash it down with a very fast rinse of acetone that smooths it out. And then now you're talking about a functional, not just a functional equivalent Lego, but one that basically has the same aesthetics. And so that technology is already readily available to everybody with a commercial desktop 3D printer. And there's something else I should point out about the Legos. Now, Lego themselves has spent years and years perfecting the mass production of Lego blocks. And they fit together perfectly, and they're awesome. But what does perfect fit mean exactly? If you're trying to make a Lego creation, you want it to last a little longer, maybe you want the blocks to be a little bit more secure. Let's say you're taking it on a roadshow and you want to make sure that if it drops, it doesn't fall apart. Well, the 3D printed Lego equivalent block, you can make the fit tighter yourself. You can control the fitness of how close they put together, so you can make it harder to put together, but then also more robust in the case of the fall. Or let's say, I don't know, maybe you have really young kids and they find it difficult to put normal Lego blocks together, you can make the fit a little bit looser, so they can also build with it. You can fine-tune it to exactly what you want, and of course you're not limited to Lego blocks. You can make anything Lego compatible now, because that code is really available on the web. So if we look at the savings, you use a recycle block to make Legos, you can save yourself a small fortune. You can see that the average Lego block price I was giving you was kind of like for a generic, just simple block. If you look at kind of the top kits, for 1,000 blocks, you're looking at spending 74 or 75 bucks. And so you can already make a significant savings off of commercial filament. But then once you get onto pellets or recycled plastic, it gets very significantly better. It's just not the toys, it's also the game boards. And so despite the fact that gaming has gone largely to electronic games, there's still a very significant market for board games. This is a $3 board game that you can completely 3D print and 2D print at home. So the game pieces themselves, the cards are all printed on cardstock. You can do it at a local print shop or run through your laser printer at home. And then the pieces are 3D printed. And if you look closely at it, there's a little card holder, there's the dice, and then there's some random action figures used to move things around. And that's where 3D printing really has an advantage. In the US, we have this sort of running joke that everybody's always fighting over the shoe for Monopoly because that's the coolest piece to use. Well, now, if everybody in your family wants a shoe, they can have a shoe. They can have different colored shoes, they can have different types of shoes, they can have a replica of their own shoe, they can have replicas of famous art, like the Vickers statue there in blue. If they have a favorite animal, there's a 3D printable version of every animal in existence at this point, and many that aren't in existence. They have a favorite superhero, they can do that. They can have whatever they want. They can make the game they want, the way they want to make it, in order to be able to play and have fun. I'm just not talking about simple games and simple toys, even more complex toys. There are many versions of drones and quadcopters that are 3D printable available on the market. One in the middle there is interesting because it uses an Arduino, a version of an Arduino, to control it. So you have it's not remote control, this is a drone that is being used off of an Arduino, that you program it yourself, you print it yourself, it breaks, you print the replacement parts. It will break, but it's useful. There is a huge expanse, millions of these designs already on the web, from things that I would consider fan art, where people are taking an idea from a video game or television show or another toy and making a different version of it. There's some from Overwatch, Monster Hunter, and Iron Man, and you're starting to see that the creativity of your customers goes beyond what you're going to allow your engineers to design because there's not a market for it. So for example, Marvel, that owns the intellectual property around Iron Man, has not made a toilet paper dispenser. Why? Because there's not a very large market for them. You certainly wouldn't want to mass manufacture that, but somebody wanted one. I don't know why, but they did. And they printed it, and it looks pretty cool, and I'm sure it's a conversation piece at their home. What about the ability for people with no CAD skills to customize products? Now, we recently had a giant fad in America for these fidget spinners. I don't know why, it just happened. And in my area, they sold out in all the stores, and so my daughter started to print them and bring them into the school and sell them for $5 a piece. Nice little entrepreneur. For printing them out for nothing. So she didn't have to understand the CAD because somebody else had used OpenSCAD, which is a script-based CAD package, to do the designs for a fidget spinner. And then Thingiverse, which is one of the larger repositories of designs, has an overlay app called Customizer, which allows anybody that knows, they don't have to know anything, can just go in and change the menus, the drop-down menus, sliders, and number things, and make their own fidget spinner. So you can have a customized product with customers that know nothing, that are then able to generate an STL and then send it to a printer. Now, Thingiverse has some problems with their licenses, and if anybody wants to talk about that after, I'd be happy to pound on them with you. But my group made an open source version of the customizer, so if any of you are interested in having customizable products based off of an OpenSCAD script or your own products, you can use our open source customizer, throw it up on your own website, and this goes for commercial entities, or if you have a nonprofit that's, say, working on like Enabling the Future does the hands, the prosthetic hands for little kids, they have a customizer app, and so now they can use our customizer so they don't have to recode it every time it sits on top of any OpenSCAD script. And so this allows you to do some really interesting things. Another professor in Britain came up with these self-reflection lenses a few years ago, and his goal was to drop the cost of eye care in the developing world. And the problem that he was having, at least with their initial runs of mass-produced eyeglasses, is they weren't cool. They weren't being taken by the students, particularly in high school, because they were kind of big and bulky, and they didn't fit the kind of aesthetic requirements of a high schooler, which is a pretty hard bar to get over. But one way you can ensure that they're met is you force the high schooler to design his own glasses. Make him make his glasses cool. Don't you try to do it for him. And so we made a customizer application with the script for that, which allows you to make your own, and then you can either leave the syringes on so that you can change kind of your prescription during the day, or you kind of write up something on the chalkboard, press the buttons until you can see, then take them off and plug the holes, and now you've got a good functional pair of eyeglasses for as little as $2. Or you can make them cool, like the little girl did down here. It's kind of a steampunk look. Her, glasses for playing and for Halloween, and they can be functional at the same time. Now, in this toy study, we found savings for consumers almost everywhere. But of those 100 most downloaded toys, there were some that didn't make any sense. We'd find like a plastic gun for some game, and there'd be cheaper, not just cheaper, but much cheaper versions on the internet. And you're like, why would anybody waste the time of CADing this thing and printing it, and then thousands of people are downloading it in this printer? Why are they doing that when they could just go to the store and buy one off of Amazon? Then we look closer. And the reason people were doing it is the guns or the plastic toys or the outfits that showed a cost savings for buying the commercial version were almost all cosplay stuff. And you may or may not be familiar with cosplay. It's when people dress up like Halloween, except more than Halloween, and they play around. And you look at the designs, and they are unbelievably good. Like, not just a little better than what was available commercially, way better. So here's some examples. Like, so that giant ridiculous gun there, that's not commercially available. People aren't selling giant toy plastic guns like this, although there is some interest in the Nerf area. The people that were doing this are really into it. They're really into their hobby, and they're sharing it, and they're using 3D printing in order to make it real. And they share those designs, so if you want like a stormtrooper helmet that's pretty darn good, you can print one yourself for almost nothing. So we kind of sum up all the trends. Right now, the open source 3D printable designs that are available on the web are growing exponentially. There are millions for sure already out there, and what that does is everybody with a 3D printer, their 3D printer is suddenly more valuable because now there's more things they can print with it. They're getting better designs, they're using less plastic, they're more easily actually printable. Just because you grab something, say, off a GrabCAD, which is this huge 3D design repository, doesn't mean it's printable. It looks cool. It was probably made for the movies or for an ad. It was not made to be 3D printed. But now there's things that are being specifically designed to be 3D printed. People are printing these designs. They're offsetting millions in purchases now. I'm very, very confident about that. And I'm also very confident that those offset purchases are going to grow with time. There's a market for desktop and prosumer 3D printers now that's growing. That market is very competitive. Many of the small players are getting forced out, but the big ones, or the medium-sized ones, are growing quite rapidly. What this means in terms of all products is that we can expect faster development cycles. Why? Because now basically every engineer that knows anything is going to have a 3D printer sitting on their desk or will have access to one. In the United States today, when you look at the job descriptions for engineers, and I'm an engineering professor, 30% of them already have the word 3D printer or additive manufacturing somewhere in the description, which means a third of American engineers of this generation are coming in expecting to know something about 3D printing. Probably using it for prototyping to begin with. And this interest isn't just in the US or isn't just in Europe or in Asia. This is everywhere. Developing countries, everyone is getting into this. So what does this mean for business? It means that in some cases, there is a growing potential that people will print rather than buy a simple object. That means there's an enormous opportunity for 3D printing sales and 3D printing supplies and services that support the ability to be able to customize an object. There's an enormous opportunity for small batch entrepreneurs for 3D printing, maybe. If people aren't comfortable with doing it themselves, they want a higher functional object, like maybe say 3D printed electronics, they're going to need to go to somebody, at least initially, to do that. If your product is 3D printable, you might need to consider an alternative business plan. If you're making injection molded plastic dinosaurs and selling them for Walmart, $1 a piece, there's some pretty nice 3D printable designs out there now, and maybe not as many people buying them in the future. There's a potential massive change in intellectual property, and we'll talk about that in a second. You might need to think about a potentially new business model, and I'll hopefully give you an idea for this. And there's going to be some pressure to move into this open source space, and I'll show you some advantages for that. So first, intellectual property. Is it relevant anymore? In the olden days, when you went window shopping, you would go to a store, you'd look at stuff that you might want to buy, and then you might go on and you might purchase it. Today, if you have a three-dimensional object and you take 30 to say 50 or 60 pictures of it, you can replicate that object completely with free and open source software or commercial software. Here's an example of this young lady going into the store, sees this kind of weird steampunkish paperweight, takes some pictures of it, turns it into a point cloud, which then turns it into a three-dimensional rendered image, which then can turn it into an STL, which can then be reprinted. Now, what happens if the thing that you're taking a picture of is a trademark toy, like, say, Iron Man? Or if it's copyrighted, or if it's patented? What happens if the consumer owns it? Are they allowed to take pictures of their own toys? Are they allowed to rip the arms off Iron Man and take pictures of the inside so they can make it fit together and move? What if someone makes the actual part? I think most people would say it shouldn't be illegal to take a picture of something, particularly if you own it. Should you be allowed to post that on the web? Well, if a bunch of people post pictures on the web, you can push them all together and make that three-dimensional object. If they print it in a single tone, does that make it okay? What happens if they print it in multiple tones? What happens if they make the entire Iron Man suit and get inside of it? What represents colorable intellectual property law in the future? What happens if it wasn't the person taking the picture, but let's say Google? This is kind of an interesting one where someone dressed as Iron Man is sleeping on a bench, and Google got them on their tripod. Or what happens if it's paparazzi? So you just need 30 pictures at different angles. You don't need it to be from the same camera. It could be from a bunch of different cameras. So somebody walks by, he's wearing some sort of weird hat, or is playing with a toy, a bunch of people take a picture of it. All those pictures then can be pushed together and to make a three-dimensional object. Did the young lady steal anything when she took pictures of an object in a store without purchasing it? Now, you might have a very strong opinion about that. And I will tell you that just based on the age of everybody in here, your opinion is probably different than your children's opinion, than to the age of the people you're selling things to. It is going to be very difficult, not impossible necessarily, to stop this. I just came from Finland, where kids use cell phones much earlier than they do in the US. So there's kids that can barely walk, munching around with cell phones, taking pictures of things and posting them on the web. It's just mind-boggling. That is soon to be displaced by kids taking those pictures, turning them into 3D printable objects and making them. And they're learning how to CAD in grade school now. So they're not just going to be taking pictures of things, they're going to be making things. And so the solution to this is, rather than think about just manufacturing toys, think about manufacturing a platform that people can then make custom products from using the platform. So you bring the customers and make them part of your manufacturing process. You purposely open source components in order to pull people in order to get them working for you, making your products valuable and better. Think about interactive toys and customization of what you can do. Focus on the parts of toys that can't be printed right now, and eventually many, many things will be printed. But as of right now, the mass diffusion of 3D printers are in plastic. Think of IKEA hacks. That's a great example where to make an IKEA hack, you need to buy something from IKEA first. Then you 3D print things around it that makes it better than the original IKEA product. And so IKEA is still selling their stuff, but they're getting people to buy more of it in order to make use of these sort of amped up versions of their products. Your customers will think of things that you never did. They will make things for a much smaller market, maybe only a couple people that you would not have captured. So this, to the best of my knowledge, is the only Iron Man bow tie. Probably not, again, a very large market for it. It, however, made somebody very happy, and they wear it, I don't know where, but somewhere. And what's interesting about this is it's not only 3D printed, it's not only, like, it definitely doesn't infringe on Iron Man stuff, because they definitely never did that or thought of it. It uses an open source microcontroller, the Arduino NeoPixel, to run it, so it can like vibrate and change colors and mess around with sound and everything. And so it's using an open source electronics, open source 3D printable design. They've shared it up on the web for everybody to use. So the market that we're all looking at in the future is with a consumer base of children that know how to CAD. They all have cell phones that are taking pictures of everything. The software to stitch together pictures is pretty good. At this point, we'll only get better in the future, and their access to 3D printers right now is at the basic level, or maybe you have to go to the library or use one at school, but because the price pressure on 3D printers has gone down, that's really opened the market up. And I don't want you to think this is just plastic fused filament stuff. The only reason the RepRap was done in that technology was because that one was patented first and the patent ran out. Well, now all the patents are running out on SLA and laser sintering, and I can guarantee you the open source community is already hacking on these devices. The price of those very expensive, like an EOS metal 3D printer laser sinter, is like $500,000. And it goes up from that. There is no way that's going to be the price in a couple of years after we start seeing laser sintering in the open source community. It's going to be in a couple thousands, and maybe we can push it all the way down. We'll have to see. The material handling on metal powders is tricky, although my own research group has made a $1,200 3D printer using one of our Delta RepRaps, turning it upside down and attaching a MIG welder to it. So you take the MIG welder out of your garage, you stick your printer underneath it, and you can start to print in stainless steel and aluminum with a resolution of about 1 millimeter. So it's not competitive with what can be done in plastic now, but it's certainly good enough for near-net shape. And if you need a metal component on the inside of something to give it structural support, that's already there now. So I think I'll end here before I get kicked off. There's just my email address and the web page for my group. All the studies that I talked about, all the designs that we've made are freely accessible and readily available. Our group actually doesn't usually do 3D printable toys. We do scientific equipment. So if you're interested in scientific equipment that's 3D printable, we've got a lot of that. So right now, Thank you very much for your time and attention. I'd be happy to continue.
Thank you, George. Now is question time. Anyone have raise your hand? We will give you the microphone. Or you can ask in Cantonese. We will try to translate for you. 大家可以用中文問都得嘅，我哋睇下點樣幫你。有冇問題？ Okay, if no question from the floor, thank you, Professor Peace again. May I now introduce next speaker, Mr. Fritz Howard, creator of Lock Lester, to deliver the next presentation. The Lock Lesters are interested in utilizing 3D printing to produce products. They utilize fabrication methodology that rely on digital file rather than physical models. They will now share how 3D printing could be applied in toy, game, and premium gift industry successfully. Mr. Howard, please.
Thank you. So, I'm trained as an architect and was in architecture school about 10 years ago when additive manufacturing, digital fabrication, kind of all these techniques were really converging in architecture schools. And got out of school, and a lot of my friends, I was in New York, or moved to New York. My friends were, colleagues were all going to work for big firms. And I knew I wanted to have my own office. I knew I couldn't get big building commissions for a while, being 25 years old. But so started thinking a little smaller in terms of what I might be able to do. So there are consulting opportunities, of course, when you're young for big companies. But in terms of having your own kind of ability to manufacture, produce, design, 3D printing was a real opportunity for me to do that. There were a lot of hurdles along the way, and I want to talk a little bit about. Is this still on? Oh, okay. Talk a little bit about taking a 3D printing product to kind of a higher end retail market, which is where the products are now, and there were a series of hurdles kind of given. So when I was in architecture school, I was producing projects that utilized a lot of computational design. So we're kind of utilized many parts. This is an airplane museum. I don't know if anyone's familiar with airplane graveyards. We have a lot of those in America in the Southwest. When the Air Force decommissions airplanes, they kind of make these massive graveyards in the Southwest. So this was a project of mine in graduate school, and utilizes a lot of computational design. So this is all kind of algorithmically positioned, the planes and the topography, and trying to think about individual discrete components and how they fit together. And I think you'll see a link between this and the actual products in a minute, but this is kind of some of the ideas in terms of design behind where the company is now. Another project kind of from architecture school, this is a cathedral, but it's thinking about the ways, architecturally, ways to compress ideas of structure, form, transparency, references to Gothic geometry, again, all kind of simulated through a series of algorithmic processes. So the idea that you can kind of control the overall design of a form computationally through a series of algorithms. So this is a pretty big switch. So then I got into the real world, and these were the kind of consulting jobs I started getting. I did a lot of advertising work. Advertisers are really into digital manufacturing, particularly 3D printing, because they can design and produce parts extremely quickly. So one of the first jobs I did was with Fisher-Price, and it wasn't a mass-produced product. They produced a couple hundred of these products, but the idea was that they would be all sourced through social media, So the idea here is they're Mother's Day trophies for moms with kids, right? So you get the plane with a spoon on the front when your kid learns how to eat, and that means you're a good mom because you taught your kid how to eat. You get the shoe when your kid learns how to walk. So companies are trying to engage through social media with their customers. You kind of comment on their Facebook page. Why is your mom a good mom? Why is your friend's mom a good mom? And the company rewards you with this kind of trophy. So in this case, we had the whole project lasted about 3 weeks. So between design, manufacturing, and mailing. And Fisher-Price was really into this idea because they can quickly engage with their customers. Another project I worked on this similar idea was with Auto Trader. Again, it's a social campaign in which big companies are always trying to engage their customers directly. So in this case, you're sending in your headshot, and we're producing very quickly turning around a series of hula dolls. I don't know about Hong Kong, but in America there's this kind of famous hula doll dancer that you put on your dash, particularly in the West. That's kind of a frontier idea, independent, drive around car with your dancing hula dancer. And that's been around for a long time. So Auto Trader is a company that sells cars or sells used cars. And the idea here is there's a social media campaign to engage with customers. You just send in any image of your face, and we're producing a hula doll in your likeness. So these are about kind of we're producing 400 or 500 of these, so we're not mass producing them, but it's something a company can do very quickly to engage with a customer base. In addition to the hula dolls, they did hood ornaments, which I'm sure you're familiar with. Each Jaguar has the Jaguar on the front of their car. Mercedes, all of every car company wants an iconic hood ornament, whether it's actually sticking out or not. So similar idea here. In this case, people would enter an idea for a hood ornament through Twitter primarily. And we picked a couple hundred, modeled them up, and these were actually printed in metal. So this was kind of my introduction into, professionally at least, into the kind of additive manufacturing world, but also the engagement world of kind of a company putting a lot of resources into this type of manufacturing. The metal pieces come out really well. They're kind of they're heavy. I think the consumer kind of has a feel that they have a lot of value to them. They have a lot of weight to them. Final thing in terms of customization, this was for Skinny Cow ice cream, which is a healthy, skinny ice cream, primarily marketed towards women. Again, a very quick campaign. I think this was a couple weeks. And we made these kind of ice cream holders that have kind of customized messages on them. This was the last campaign I think I worked on, but just a couple-week turnaround. You can submit your ideas, your photos on social media, and get these really quickly. So I did a lot of that consulting for a while, and was looking for a way to turn to my own business, to do my own design work. And the kind of parallel back to my work in design school was that in a computational design sense, I was always working with kind of many pieces kind of coming together to form a building, or to be simplified into one piece. And the idea of kind of using those similar types of algorithms I developed in graduate school to make an interlocking physical part was one that came quickly, and one that needed the printer to be able to prototype, to be able to be prototyped quickly. So if you think about kind of three-dimensional connections, there are a whole lot of three-dimensional connections that are used in the toy industry, the construction industry. There's kind of a couple of different, I guess, broad categories of ways to go. The the most widely used is the component method, where, I mean, in the top center is an example of a component type of fabrication. But one of the engagements with the 3D printer I wanted to work on was the ability to have completely customized parts for every unit of a toy, or even larger a building. So at the time I was doing a lot of 3D printing in ceramics, which was kind of an altered form of an early Z-Corp machine. You could print in ceramics, you could fire that print, and the idea was if you could print and fire a ceramic, you could print a brick, and then you could print a facade for a house. As long as you're doing that, the printer doesn't care if you're printing a standardized brick or a completely custom brick. The trick there is to have a software method to output fully custom parts immediately, right? So the trick there is not on the hardware output; it's in the software development. So these kind of the bottom two examples here are the first tests I was thinking about in terms of how could you break up a sphere with a series of custom parts, and you could reduce those pieces as simply as you could a set of components. So I'm just going to. Okay, thanks. So this is kind of a sketch of an idea in which you have a couple hundred pieces. Each piece has 5 arms, and they start to reach out and wrap around one another. Right, so they all have kind of an intelligence of a relative proximity to one another. You can see at the end of the sketch, most of the screen is full, and all of the pieces kind of have developed a proximity to their neighbor. So if you take this idea as the basis for a set of components that can then be broken up, they can be put through a 3D printer just as easily as any kind of standardized part can be put through a printer. So the idea is you start with a three-dimensional model. Doesn't matter what it is. The algorithms run across the surface of it, and you end up with these forms that I call center lines. Just make this. I'll make this full screen. Control. Oh, okay. So each one of these would represent kind of the end manifestation of the animation we just saw. And they're the kind of centers of the arms of each piece. So then if you think about adding these red lines, this is the thickness of the piece, and starting to think about how they hold together, right? So this is the exterior of a mesh that would be hollow on the inside, and would be a variable thickness, a couple between 1 and 3 centimeters. The idea being that this is going to form a customized skin that could be applied to the scale of a building, depending on the material you're printing, the scale of a product, or for a toy. So here's kind of the individual piece with a variable thickness depending on the curvature that it's going across. So I didn't do a building first. I developed a dog, which was the kind of first form I applied it to, and I'm not sure how evident this is, but kind of these two examples on the left are very organic forms, right? They're very curvaceous. The pieces kind of fit in a kind of more unwieldy way. Whereas the example on the right, there's many more kind of parallel connections. And this was kind of a development in terms of the research process of figuring out how to make this this three-dimensional interlocking set of pieces that could both come together and come apart afterwards. So the first one I made, I put it together and put it in my friend's hands, and it just completely fell apart. The second one I made, I put it together and I couldn't get it to come apart. So this kind of prototyping stage was entirely made possible by the 3D printer, and led to these kind of parallel relationships between the pieces on the dog on the right. Those kind of got distilled into 3 types of connections. that you can see on the left side of the page here. And they really kind of change depending on the complexity of the curvature that the piece is traversing. So part of the project was to be able to deal with a mesh of variable curvature, and for the algorithm to create different types of connections depending on the curvature it was traversing, right? So you can imagine if your mesh has a very tight curvature and your pieces are traversing most of that, the connection is going to be very different than if your mesh is kind of smooth and constant, and you have a very small set of pieces. So these got distilled into a set of figures, and they were called lock nesters. There was 5 figures in the first set. You can see them kind of here. There's a pig, a duck, a bear, a dinosaur, and a dog. So at this point, I was completely distracted from the idea of making a building. And that was, I didn't mean to kind of, I wasn't expecting to go this route, but the success of the dog kind of led to other figures. You can see kind of in different ways the way the algorithm is kind of running up and down the length of the dinosaur. It's kind of curling around more on the bear and the duck. So depending on the properties you give the algorithm, it'll divide the mesh in different ways. And this project was actually launched on 3D Hubs, which our previous speaker I'm sure is familiar with. The idea being that you could buy these STLs, you could buy the files, and you could print them in your house. And so it was a distributed manufacturing idea. So you get kind of these, the 20 pieces, I think the dinosaur is 21 pieces of the dinosaur. You'd print them at your house, you'd take off the support materials, and then you'd have the dinosaur there. And that was successful. We did that for about a year. And, but I was never kind of, the intention for this, part of the research project for lock nesters was to test the idea of the potential of a 3D printed product on a low-end machine, and these are all kind of entry-level FFF machines. Is there a way to get that part into a higher-end retail kind of solution? So this was the dog. He's 27 pieces. They kind of came with this semi Lego style assembly sheet. His name was Otis. And this was kind of the end manifestation of the research. He's a bust of George Washington, and he's about 200 pieces. So this example is not mass produced, but kind of it's an example of putting having the bust into CAD, right, and then letting the algorithm divide the bust into a series of pieces that are then able to be assembled. So he's about this tall, and he's about 1/3 of an inch thick. So it's really, if you imagine wrapping a jigsaw puzzle around a 3-dimensional figure, and each piece is unique, right? So if you think about applying this algorithm to different meshes, you know, the idea of molding pieces didn't make a lot of sense at the time because you're only producing each piece one time. So printing was kind of the avenue for being able to deal with this type of customization. So the first kind of big job I got with this idea was with Yahoo, which used to be going strong, and that was I think this job was in 2014. And this was kind of another case of the need for a quick product. This project was about 3 weeks long. They were having kind of a huge company retreat, and they wanted to have like a dinner company employee team building exercise for their dinner. So we took the exclamation mark and basically divided it up in the exact same way that I've been talking about. I think this puzzle had 27 pieces, hollow core, just like the earlier examples I was showing. and we made about 120 of them. So again, not a huge run, but we were able to go from design to manufacturing to delivering in about 3 weeks, which was great because in terms of prototyping, each piece needs to be prototyped a couple times, and then when it's set, we were able to do all the production locally and get them to this conference quickly. I don't know if you've seen Silicon Valley. This actor's from Silicon Valley. He didn't like the he made fun of the puzzle during his set, which was after dinner. But that's okay. I still like the show. But that was kind of the first proof of concept for kind of a commercial use for the puzzle system, for the algorithm, and one that could kind of be a purely unique product and turned around in a very short period of time. Here's kind of the progression of building that, and I think we made about 120 of them. So that brings me to kind of where the products are now. So these are the current lock nesters. So kind of going back to my the origin of my previous figures. So I was, if you remember the kind of image I showed of the colored figures that were on 3D hubs, they did well on 3D hubs. I wanted to kind of see if I could get this into a higher end retail market. So I'm kind of focusing on these two figures and really started focusing on different quality of finishes with 3D parts and figuring out how to get it to an acceptable level for kind of a design store, a home decor store, which is where they're sold now. So you can see, so these are some close-ups of the bear. The kind of complexity of the algorithm is not so present. It's a simple toy, but the quality of the finish and kind of the fit and the feel became extremely important for kind of going into higher end retail stores. So we tried a couple things. So these are all printed in PLA, polylactic acid. One of the, I guess, the biggest thing we had to tackle at first was the finishing technique. And we did that through a series of investigations. There are a lot of chemical processes that you can try out. And through my experience, that's much more successful with an ABS print. We ended up working with a mechanical process of simple barrel tumbling, which harkens back to kind of, which starts to combine kind of advanced manufacturing techniques of printing and more traditional methods. Barrel tumbling is something that we've been using for years and years and years to finish products in a high-end way. So the pieces kind of come off the printer. They're super rough. They're made on kind of an entry-level machine. It doesn't matter what the machine is. They get sanded down, and then they go in the barrel tumbler for a long time. When they come out, they're dirty. They kind of have gunk all over them, and they're wet. And then they go through another tumbling process that kind of cleans and buffs them off. And then they get a lacquer spray to finish them. So the process kind of evolved to something where we're starting with a kind of a high-end digital manufacturing technique, and then we're starting to combine kind of older established manufacturing finishing processes to get it to a point where we can go into a higher retail setting. So kind of a couple examples of on the top left, when they're coming out of the barrel tumbler, they're dirty. They're kind of caked with a material that has to be removed. So they're going through another tumbling process to kind of get cleaned down, and then eventually they're lacquer sprayed.